Welcome to this fascinating journey into animal behavior. Today, we are going to explore one of nature's most spectacular events, the formation of a new honeybee hive. We will discover exactly how a single colony divides itself and makes highly intelligent collective decisions to ensure its long-term survival. By the end of this video, you will understand both the biology and the mathematics behind this incredible process. To truly understand how a hive forms, let us start with a simple analogy. Imagine a bustling, highly successful city that has grown too large for its own borders. The resources are stretched thin, the streets are overcrowded, and there is simply no room left to build new houses. What do the citizens do? A large group of them decides to pack up, follow their leader, and establish a brand new city somewhere else. This is exactly what happens in a honeybee colony. It is a spectacular natural event where a single superorganism divides itself in half to reproduce. Now that we have the big picture, let us look at the biological mechanics of this process. Swarming is not a sign of a failing hive. It is their natural method of reproduction. When the colony becomes severely overcrowded, the worker bees take action. They begin rearing new queens in specialized peanut-shaped wax cells called queen cups. But before these new virgin queens can even emerge, the old mated queen leaves the hive. She takes roughly half of the worker bees with her to find a new home. This massive departing group is what we call a primary swarm. While the primary swarm is looking for a new home, what happens to the bees left behind? The primary swarm will temporarily cluster on a nearby tree branch, while scout bees search the environment. Meanwhile, the remaining bees in the original hive are waiting. They wait for a new virgin queen to hatch from those peanut-shaped cells. Once she emerges, she must eliminate her rival sisters to secure her throne. After that, she will fly out to mate, return to the hive, and take over the egg-laying duties to rebuild the original colony's population. This dramatic division is not just a biological curiosity. It has massive implications. In nature, the formation of a new hive is absolutely critical for the survival and genetic dispersal of honeybee populations. Without swarming, a colony would outgrow its space, become highly susceptible to disease, and eventually collapse. However, in the realm of agriculture, swarming presents a challenge. When a hive swarms, it temporarily stops producing honey and pollinating crops, which directly impacts human food security. Because of this, beekeepers must actively monitor their hives for signs of swarming to prevent the sudden loss of their workforce. So the swarm is hanging on a branch, waiting. How do they actually choose their new home? They rely on scout bees and a brilliant process of collective decision-making. When scouts find a potential site, they return to the cluster and perform a waggle dance. If the site is excellent, they dance enthusiastically, which creates a positive feedback loop, recruiting even more bees. This causes the number of bees at a good site to grow exponentially. Once the number of bees at a specific site reaches a critical threshold, known as a quorum, the entire swarm lifts off to move in. Now that we understand the concept of collective decision-making, let us look at how we can model it mathematically. The formula for this is n of t equals n0 times e to the power of r times t. This equation comes from the natural continuous growth we see in biology. Let us break down the symbols. N of t is the total number of scout bees at any given time t. N0 represents the initial group of scouts who found the site. The letter E is the base of the natural logarithm. The variable R is the recruitment rate, which depends on how enthusiastically the bees dance. Finally, T is the elapsed time. Physically, if the recruitment rate R increases because the site is excellent, the total population skyrockets rapidly. Before we move on, let us see this formula in action with a concrete example. We are given an initial group of 5 scout bees, so N0 is 5. They dance enthusiastically, giving a recruitment rate R of 0.5 bees per hour. We are asked to find the total number of bees after a time T of 4 hours. We choose the exponential model because it perfectly captures how the positive feedback of the waggle dance accelerates population growth. First, we substitute our known values into the exponent, multiplying 0.5 by 4 to get 2. Next, we evaluate E squared using a standard calculator, which gives us approximately 7.389. Finally, we multiply this by our initial 5 bees. The final answer is approximately 37 scout bees. Physically, this means the site has surpassed a typical quorum threshold, and the swarm will soon take flight. This successful calculation leads us to an even more fascinating scenario. What happens when the swarm has to choose between 2 competing sites? In nature, scouts often discover multiple potential homes simultaneously. Imagine Site A is mediocre. It was discovered by a large initial group of 10 bees, but because it is mediocre, it has a low recruitment rate. On the other hand, Site B is excellent. It was discovered by only 2 bees, but its high quality triggers a very high recruitment rate. The swarm must make a democratic decision. The winning site will be the one that reaches the quorum threshold of 50 bees first. This sets up a beautiful mathematical race between initial numbers and exponential growth. Now that we have set up the race, let us calculate exactly how long it takes for the mediocre site A to reach the quorum. We are given a quorum of 50 bees, an initial population of 10, and a rate of 0.2. We need to find the time. We set our total population to 50 in our exponential equation. To solve this, we first divide both sides by 10 to isolate the exponential term, leaving us with 5 equals e to the power of 0.2 times time. Next, we take the natural logarithm of both sides to bring our time variable down from the exponent. Finally, we divide the natural log of 5, which is 1.609, by 0.2. The final answer is 8.04 hours. This is the time Site A needs to win. With Site A's time calculated, let us perform the exact same steps for the excellent Site B to see who wins. We are given the same quorum of 50, but an initial population of only 2 and a much higher rate of 0.8. We set up our equation and divide both sides by 2, giving us 25 equals e to the power of 0.8 times time. We take the natural logarithm of both sides again to remove the base e. Dividing the natural log of 25, which is 3.219, by 0.8 gives us our final answer. It takes Site B just 4.02 hours to reach the quorum. Physically, this proves that despite starting with fewer bees, the higher quality of Site B led to faster exponential growth, allowing the swarm to intelligently choose the best possible home. To visually reinforce what we just calculated, let us look at this diagram of the swarm nest selection process. On the far left, you can see the original hive with a queen cell, which initiated the swarming. The bold arrow points to the primary swarm, clustered temporarily on a tree branch. From this central cluster, you can see scout bees flying out to 2 different locations. Notice the top right. Site A is a small, mediocre birdhouse. Only a few dashed arrows point to it, representing the low recruitment rate we calculated. Now, look at the bottom right. Site B is a large, excellent hollow tree. There is a thick, heavy stream of bees flying towards it. This diagram beautifully illustrates how the higher recruitment rate for an excellent site quickly overpowers a mediocre site, leading the entire swarm to their optimal new home. We have covered a lot of ground today, so let us summarize the key takeaways from this topic. First, we learned that swarming is a vital biological process that relieves overcrowding and ensures the genetic expansion of honeybees. Second, we saw how the old queen leaves with a primary swarm, while scouts use waggle dances to recruit others to potential new homes. Finally, we discovered that this collective decision-making follows an exponential recruitment model, ensuring that the highest quality site always wins the race to the quorum. You have now mastered both the biology and the mathematics of hive formation. Excellent work.